Launching a satellite into orbit is a problem of sheer physics. Launching human beings into the vacuum of space and returning them alive introduces an entirely different threshold of engineering. It requires a strict zero-fail architecture that historically only 3 nations on Earth have managed to build and operate independently. The United States established the early baselines for orbital mechanics and life support. Russia developed the foundational, highly reliable crewed launch vehicles that have serviced orbital outposts for decades. And China has steadily built out its own sovereign infrastructure to deliver crews to its independent space station. ISRO's Gaganyaan mission is the rigorous technical validation required to add a 4th name to that list. It tests the specific infrastructure needed for India to field a sovereign human spaceflight program. The operational parameters for Gaganyaan are highly specific. The primary mission objective is to launch a crew of 3 astronauts into space for a duration of 3 days. The target destination is a low Earth orbit, maintained at an altitude of exactly 400 kilometers above the surface. The final, and arguably most complex phase, is decelerating that mass from orbital velocity to ensure a safe atmospheric reentry and a controlled splashdown. That splashdown must occur within a precise recovery zone located in Indian seawaters. You cannot simply take a standard heavy-lift rocket, remove a communication satellite, and bolt a crew cabin in its place. To achieve these exact parameters, ISRO had to strictly reconfigure its reliable LVM-3 rocket into a highly redundant, fault-tolerant architecture. The result is the Human-Weighted Launch Vehicle, or HLVM-3. To understand the HLVM-3, we have to look at how it is built from the ground up, starting with the primary lift mechanisms. The first stage relies on 2 massive solid-fuel boosters attached directly to the sides of the central core. Solid propellant is used here because it delivers an immediate, high thrust-to-weight ratio. That brute force is required to fight the densest part of the lower atmosphere and overcome initial gravity. Between those boosters sits the central core, which operates as the vehicle's second stage. This stage is powered by a pair of liquid-fueled, clustered Vikas 2 engines. Once the rocket clears maximum dynamic pressure, the point during launch where aerodynamic stress is highest, the vehicle requires controlled, sustained acceleration. Unlike solid boosters, which burn continuously until depleted, liquid engines like the Vikas 2 can be throttled and precisely managed to shape the ascent trajectory. While these first 2 stages provide the power to leave the lower atmosphere, achieving a precise 400-kilometer orbital insertion requires a more complex chemical reaction. That brings us to the 3rd stage, positioned directly atop the liquid core and just below the payload fairing. This section houses the CE-20, an indigenous cryogenic engine designed specifically for high-efficiency orbital injection. Cryogenic propulsion relies on a highly volatile mix of propellants. The CE-20 uses liquid hydrogen, acting as the fuel, and liquid oxygen, acting as the oxidizer. The engineering challenge here is strictly thermodynamic. These propellants must be stored at ultra-low temperatures while sitting adjacent to a combustion chamber generating immense heat. Igniting this supercooled liquid mixture in the near vacuum of the upper atmosphere and instantly converting it into high-velocity plasma requires exact timing and flow control. Mastering this indigenous cryogenic technology was the critical engineering bottleneck ISRO had to solve to independently lift heavy, human-rated payloads into low Earth orbit. With the launch vehicle fully stacked, the focus shifts to the payload section mounted on top. This is the orbital module. It is a self-contained spacecraft engineered to replicate an Earth-like environment in the vacuum of space. The environment is partitioned into 2 distinct halves. We will start with the lower section, the service module. The service module operates as an unpressurized bus. It handles the spacecraft's in-orbit propulsion, power generation, and dissipates heat through thermal radiators. Crucially, it also carries the heavy consumables, the large water and oxygen tanks required to keep the astronauts alive. Sitting directly above that is the upper section, the crew module. This is the fully pressurized habitable zone, where the 3 crew members live, work, and monitor the spacecraft. Integrating this space requires tightly packing the environmental control and life support systems, alongside the mechanical parachute bays necessary for the return trip. Together, the orbital module functions as a bipartite microplanet. The upper crew module protects the humans, and the lower service module keeps them alive. But placing humans atop hundreds of tons of combustible rocket fuel requires a way to extract them immediately if something fails. This introduces the final component of the HLVM-3 stack, the Crew Escape System, or CES. The CES is an autonomous safety mechanism. Its singular purpose is to save the astronauts' lives in the event of a catastrophic anomaly during launch. In an abort scenario, the solid motors in the CES tower ignite in milliseconds, physically ripping the crew module away from the failing rocket. Because this extraction generates extreme G-forces, the crew module itself had to be massively structurally reinforced just to survive its own safety mechanism. The successful integration and reliability of this escape system is the definitive engineering threshold that transforms the standard LVM-3 into a human-rated launch vehicle. What ISRO has assembled is a fully integrated, human-rated heavy launcher, carrying a dual-component orbital module and capped with a dedicated instantaneous abort system. Before humans are allowed on board, this exact architecture must be successfully flown in 2 uncrewed validation missions to prove the system's engineering holds up under live launch conditions. The nominal flight profile demands exact sequencing, the staggered ignition of the solid, liquid, and cryogenic stages, culminating in insertion into the 400-kilometer orbit. The return profile requires the service module to separate cleanly, allowing the crew module to survive atmospheric re-entry before deploying its main parachutes. Gaganyaan is a chain of thousands of strict mechanical dependencies that must execute sequentially, flawlessly, and without hesitation over the course of 72 hours. Looking beyond the immediate hardware, this mission serves a much larger strategic timeline for ISRO. Mastering independent LEO operations is the mandatory precursor for undertaking advanced robotic sample return missions from other celestial bodies. And ultimately, this architecture provides the heavy lift and life support framework necessary to construct and supply the planned Bhartiya Antarctic Station. Geopolitically, possessing an independent human spaceflight capability elevates India's diplomatic leverage, allowing it to negotiate international space collaborations as an equal partner. Domestically, building this hardware drives high-tech manufacturing, creating localized economic growth and highly specialized employment. It forces the creation of an integrated structural partnership between deep tech academia and private industry, backed by the resources of the state. Gaganyaan is not the finish line. It is the foundational infrastructure required to secure India's sovereign position in the next era of space exploration.